Hi, in this video I want to give you some background about mass spectrometry. Now, mass spectrometry is just a technique, an experimental technique to measure masses of atoms and molecules. And from the mass we can figure out possible chemical formulas. Now, mass spectrometry can be performed in many different ways, but essentially they all have some things in common. So here's a short video to explain the basics of mass spectrometry.
The mass spectrometer is a vital instrument in many kinds of chemical analysis. But how does it work? And how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer, we use electromagnets to try to deflect the ions off their path. The amount of force that the ion feels from the electromagnet is proportional to its charge. The path that the ion actually takes is a result of its mass-charge ratio. A different particle with a different mass-charge ratio will take a different path. And this is what we are actually detecting, different mass-charge ratios. So let's analyze a sample. We vaporize it and ionize it, accelerate it, deflect it, and then detect it. We can record its mass-charge ratio. If we repeat this with more of the same sample, we will record different size fragments. Eventually, we'll know the proportions of all the different size pieces in our original sample.
So the heart of the spectrometer is right here, where the ions are separated by mass. And in this example, carbon dioxide is being analyzed, and we see 3 different masses. Now, our data would actually come out of the spectrometer in a graphic format where we would see the mass, the charge ratio on the x-axis, and the abundance, or the quantity or number of ions, plotted on the y-axis. And in this example we might see some lines that where this was the 44 mass per charge ratio, and then there'll be some smaller peaks, maybe something like this and like this, or this is the 45 and the 46. So what's going on here? Why are there 3 different masses for carbon dioxide? Well, carbon has 2 main isotopes. Remember, isotopes are elements with the same number of protons but different numbers of neutrons. Well, and for carbon there's some atoms that have 6 protons and 6 neutrons, and since a neutron weighs about the same as a proton, the mass is 12. And there's another isotope, carbon 13, where there's an extra neutron. There's 6 protons here, 6 neutrons, and 6 protons here, and 7 neutrons. And of course the identity element is determined by the number of protons, and the neutrons are just dead weight. It's just making them heavier. Let's see, oxygen isotopes. Well, there's also 2 main isotopes. There's oxygen 16, let's see, 8 protons, 8 neutrons, and there's oxygen 18, 8 protons, 10 neutrons. Okay, so it's 2 mass values heavier, and they're not in equal proportion. It's about 99% carbon 12 and about 1% C13, and it's about 99.5 or so of oxygen 16, and about 0.5% of oxygen 18. And so where are these mass values coming from? Well, if in CO2 there's 1 carbon 12 and 2 oxygen 16 isotopes, which is most likely since most of the oxygen atoms are going to weigh 16, right? Most of the oxygen atoms are of isotope 16, and most of the carbon is going to be isotope 12. Well, 12 plus 16 plus 16 is, there's an equal sign there, is 44. But occasionally there might be a C13 that sneaks in there. In which case, if you add up those numbers, the mass is going to be 45. Or we could have carbon 12, oxygen 16, and one of the less common isotopes of oxygen, oxygen 18. And in this case, the mass is going to add up to 46. Now you might be asking yourself, well then, can't there also be some carbon dioxide, sorry, CO2, where you have the C13 and the oxygen 18 and the oxygen 18, in which case what are you going to add up to? It's going to be 49. And yes, technically you could have some of that, but that's asking for about 1% of the carbon to show up in this molecule at the same time that 0.5% of the oxygen shows up, at the same time 0.5% of the other oxygen shows up. And if you multiply those together, that's your probability that all three heavier isotopes are going to show up in the same molecule, and that's going to be a small number, right? Okay, that's going to be a real small percentage. That's 0.01 times 0.005 times 0.005, and let's just get my calculator out. Okay, so that's a pretty small percentage here. Okay, that's the background you need for mass spectrometry. Essentially, it's a place where you insert your sample. It gets ionized. Well, first it gets broken up into small particles and then ionized. And once it's ionic, then a magnetic field or electric field can add force to it. And so these placed down here are going to be, I think they're electrified. If you have positive cations, then you get a positive charge in here, so you repel those ions and send them into the chamber. They pass through a slit, so you got a nice narrow beam, and then they enter a magnet in this case, this example, and then they're sorted by charge, so they can go through the slit, and the detector here detects it, and then we can measure their masses. That's magnetic sector. And this heated filament here is the electron impact method for ionizing. And there's a couple different detectors down here. Essentially are detecting charges, ions. And then for the chem majors, there's more video here explaining electrospray and MALDI, matrix-assisted laser desorption ionization, as well as time of flight and quadrupole methods. And if you're interested, you can stay tuned for that. Otherwise, you've got the background you need to understand mass spectrometry.
Have you ever heard of electrospray? This aerosol technique has many existing and potential applications, and among them is the making of dry and fine deposits of substance. Electrospray starts with a liquid formulation, pushed through a capillary at a precise and constant flow. When an electric field is created by wiring the liquid to a high voltage, the meniscus rapidly turns into a stable cone, out of which a jet of liquid emerges and becomes a stable spray. This is the cone jet mode. Primary micrometric and highly charged droplets are formed in the jet. Due to electrostatic repulsion, they break into finer charged droplets, which themselves break into smaller and smaller ones, thus becoming nanometric.
The Maldi-Toff process is a two-phase procedure. Initially, the samples are fixed in a crystalline matrix, In the initial ionization step, they're bombarded by a laser. The sample molecules are vaporized into the vacuum while being ionized at the same time. High voltage is then applied to accelerate the charged particles. The second step is the time-of-flight mass spectrometry phase. In the linear mode, particles will impinge upon the linear detector within a few nanoseconds after ionization. Higher mass molecules will arrive later than lighter ones. Flight time measurements make it possible to determine molecule masses directly. Each peak in the spectrum corresponds to the specific mass of a particle along the time axis, starting with the ionization moment.
Today we'll be looking at a special kind of spectrometer called the quadrupole mass spectrometer. It's called this because of the 4 long poles that make up the center of the instrument. So say you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting a piece called the ion source. Here, a stream of electrons hits the molecule, breaking it into fragments and giving each fragment a charge. Next, the fragments enter what's called the analyzer. Here, they're separated based on their mass, and the analyzer is tuned so that only the fragments we want to see make it all the way through. Everything else flies off in a different direction. After this, the fragments hit what's called the detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. And here, the real work begins. The mass spectrometer is a powerful tool, and by taking many samples, looking at the results, and studying what we find, scientists can work to discover not only the secrets of water and life on Mars, but also answers to bigger questions about the universe. And all by studying something as tiny as a molecule.